I'm happy to talk about our research topic. I shortened the title a little bit, Sensing Machine Elements as an Enabler for Comprehensive Digitalization. Motivation and vision of that presentation. We all know that there's a lot of discussion about added value through Industry 4.0. What does that mean? Additional value is made available by gathering new information, preferably without adapting complex new technology, rather than exploiting the sensors and signals that are available in the machines. This enables the usability of cyber-physical systems, CPS, and predictions, for instance, about required maintenance based on big data. The necessity of reliable data acquisition close to the process is obvious. We want to measure not as much as we can, but as good as we can. The idea now is that we use our machine elements, basically the atoms of our mechanical design, here a rolling bearing, integrate those into a system, here a simple single stage transmission, and use them as a sensor. The data which is acquired can be fed into the digital twin. For instance, here, the digital twin of that rolling bearing, special type, 6205 C3, dimensions, material, we have the mounting position, and we can apply or connect also a mathematics model. Here, the model is for calculating the lubrication film in the rolling bearing and its interaction with an electric field. The real part and the digital twin together make up the CPS, the cyber-physical system of that rolling bearing. And to be honest, nobody really cares about how does a bearing feel. The real quantity of interest is the transmission or the system in which the rolling bearing is applied. That's the motivation, that's the vision. We want to measure in the machine element and provide this information to system level control in a reasonable way. Structure of the following, around about 18 minutes. After that discussion, I will briefly touch base on digital twin, prototype and shadow, and then talk about data value and veracity. What do we mean? Measurement locations are important to understand what options we have for applying our measurement system. Then we will go into the classification of machine elements. This leads us then to the benefits and challenges of next generation machine elements, which have an additional functionality in the field of sensing technology. I will conclude with an outlook to the remaining obstacles to bring those ideas into production. The digital twin, we start with a digital master. This is our CAD model of our plant, of our machine, of our rolling bearing. From that, during the production, we can derive a digital master. This is still our CAD model. We have the digital shadow, which is representing a specific product, whether it's a rolling bearing, a transmission, or a plant. It's the same, but it's different levels of complexity, however. Now we can have, out of the same digital master, we can derive digital twins for various instances of, for instance, the same production part number, simply different digital twins of different products. And also at the end of the useful life of our product, we can use those digital twins and learn, for instance, what was the accumulated mileage, so to say, for that bearing. Can we still use the component? Is it good for a second life? And so on. When it comes to the data itself, we have this model here, the 5V model. It was presented by IBM in the beginning, and it's a model to quantify the important aspects, important characteristics, especially for big data volumes. Data volume is obvious. That's simply the amount of bytes, bits, megabytes we need to store Velocity, that's in our case related to the frequency, for instance. We measure temperature and acceleration with different frequencies, and that needs to be taken into consideration. The variety, for our purposes, it's the sensor perspective. Is it a temperature, which we record, or a picture? Important is the data value. Is this really data, or can we yet get information from that data? That means we have managed the first level of extraction of information, reduced the data to information, or can we already gain knowledge from the measured data? Data veracity simply means, can we trust the data? Is it reliable? Is it repeatable? Etc. With that in mind, we now look to the different measuring locations. I've chosen as an example from my industrial career. Jörg mentioned that I was responsible for the transmission development here in Valeo Siemens before I joined the academia. We have a single gear stage. We have an electric motor, an inverter, a non-switchable two-shaft transmission, and a little differential. Now the task is that we want to measure the output torque, which is relevant for the vehicle dynamics control. Different measurement positions are possible. We can start, for instance, to measure the current, the power supplied from the battery to the inverter. Here we measure voltage and current in the direct current region. Take that as a number 1. Following the power path, the next position is at the outlet of the inverter, at the inlet of the stator. Here we have, again, voltage and current, but now in the alternating current regime. We have gone through a cycle of energy transformation. Now we have gone from direct to alternating current. Now we are close to process. Here we are far from process. Again, when we follow the power path, we end up here in our side shaft. Here we are now in the in situ position. That's really the quantity of interest. We want to measure the torque at the wheels or at the axle in order to be able to perform high quality control of our drive system. We're directly measuring in the power transfer path. Now the target, the quantity of interest, speed and torque. So that's our target. We want to measure in situ, really in the working process, and not at a close or a far away position. That's the target for our measuring location. And now the question arises. Imagine we have tooth wear. Can we also detect tooth wear by a similar measuring philosophy? That's the challenge. Now we look to that tooth wear. We start to analyze how we can really detect the patterns in our system. We have the first measuring location, as it is usually done, somewhere ex situ, off process. We have the target quantity, our vibration of the torque, which is caused by the pitting here, for instance. And we have our measuring chain. Here we have the received signal, which can be used to really, derive from that data, knowledge, information and knowledge. With the in situ measurement, the measuring chain looks very much the same. But now the point is all about disturbances. At the ex situ position, we have a lot of different disturbances which can have an influence on the data received by our control system. We have to understand all those different mechanisms of the disturbances and their effect on the measuring chain. For instance, here the mechanical path of the transmission. We have production tolerances. We have the effect of a transmission lubricant. We have splash, we have drag. In the electric circuit, we have losses in the copper, conversion losses, etc., which we need to take into account. If we now apply our in situ measurement, we all of a sudden see that we have here our sensor, and we have eliminated quite a bunch of uncertainty and their effect on the measuring result. However, we still need to understand the remaining disturbances and their impact on our signal, and that's part of our research. With that in mind, we now look to the machine elements. Machine elements, probably think, why do we need to classify those? There are shelves of textbooks available which describe all those machine elements. Yes, that's true. We have our conventional machine elements. That's the shelf of bookstores, or the bookstores we have. But mechatronic machine elements, that's the novel aspect. Now we bring the machine element into a control circuit, and we make this machine element all of a sudden talk to our controller, to sensors, providing data, being part of the communication cycle. We can differentiate the mechatronic machine elements into actoric machine elements and sensing machine elements. We will focus here on the sensing machine elements for a very simple reason. If we look to the obstacles at the end, we see that energy and data supply and transfer is the most challenging question. Now we have here for a sensor, we have a few milliwatt power supply. For an actuator, we have completely different orders of magnitude of energy which need to be provided. And that makes the story here much more difficult. So we start with the sensing machine elements as a discussion base. Now we can differentiate those further. We have sensor carrying machine elements, and I will give an example on the next slide. We have sensor integrating machine elements, and this is what we are trying to push forward with our research together with other universities in Germany. And we have sensory utilizable machine elements. Here we have an effect which can be used as a sensor itself. Let's look to the examples which makes it more clear. The sensor carrying machine element, here we have the mechanical function of the machine element, and the sensor, annotated by that yellow box here, has no real connection to that machine element. We have simply a machine element carrying a sensor, that's what the classification says. The sensor integrating machine element, we have now a connection between our mechanical function. Here's a data path to that sensor. All of a sudden the sensor is affected, the sensor signal is affected by the mechanical function. For the sensory utilizable machine element, we have the mechanical function and the sensorial effect being closely tied together. We cannot distinguish between the sensory effect and, for instance, the tribological layer. Here we have an example. The sensor carrying machine element is simply take a bolt and apply a temperature measuring device, thermal element, to that bolt. The bolt carries the thermal element, the thermocouple, and that's it. There's no relation between the temperature measured and the mechanical function of that bolt. Here we have a sensor integrating feather key. It's a prototype, but it worked. Now that sensor integrating feather key provides a voltage signal as an output, which is dependent on the torque transferred by the feather key. And finally, here we have a sensor integrating, or a concept of a sensory utilizable journal bearing. We use the lubrication film here between the shaft and the bearing as a sensor. We measure the capacity. That's the idea. With that in mind, we start to look to an example. Here, for instance, a picture from SAP Eurodrive. The idea is to monitor that gearbox. Typically, we apply a accelerometer somewhere to the housing of the transmission. In order to simplify the following pictures, we have chosen here one of our demonstrated transmissions, which is much less complex, but still shows all the effects. We have our mechanical path. We have here a two-step gearbox, input shaft, output shaft, intermediate shaft. Here we have our tooth failure, and that tooth failure, we assume it, now is communicated to our accelerometer on the housing via two different transfer paths. The first is via the intermediate shaft and its bearings, and the second path is via the output shaft and its bearings. So we have a non-unique transfer path from that damage pattern here to our accelerometer. If we now apply our sensor integrating machine elements, we still have the same structure. We have our input shaft, and now that input shaft comes with its own CPS, with its own cyber-physical system. We have a sensor integrating shaft coupling, for instance, and a sensor integrating feather key. The same for the intermediate shaft. We have two of those feather keys. The output shaft, again, a feather key and a shaft coupling. And now we can read from our tooth pattern, tooth failure here, directly, for instance, via that feather key or the other on the output shaft. We have much more direct possibilities to read the signal of our sensors and to interpret those. Looking to the challenges in the sensor, a quick comparison. I have to look onto the timing. We have here a smartphone. Many of you know the problem when the smartphone falls down, the sensors get wrecked. Now we have here a typical falling experiment 500G. If we apply the same sensor technology from the consumer product to, for instance, a belt drive system, we have now 500G at every disk in our belt drive system. Now, all of a sudden, we see that the load profile gets much worse for the application of one and the same sensor, which is working in the smartphone when we implement them into a machine element. Here in that case, we have calculated up to 5,000 G acceleration load on the sensor. Looking to the rolling bearing, we have here the example. We see that the outer ring, the inner ring, and the rollers, we have a complex network of capacitors. The model is that we interpret the heads and contact area as a capacitor, and from that we have now to reduce the complexity, the uncertainty. We have to, for instance, include the lubrication film thickness at unloaded rollers to improve the the model quality. We have to include the complex geometry of the heads in contact. And if we take a lot of data and feed them through a neural network, we end up all of a sudden with a pretty accurate way to interpret the measured capacity as a load sensor. If we apply that system into our single stage transmission, here we have our bearing, our sensor. We measure the impedance, and we can read from that bearing forces, lubricant condition, and bearing condition. The design requirements is that we have a proper insulation of our rolling bearing, and with that we can start to read now in the transmission. And here we have a plot of different measured impedances versus torque level. It's not really a linear relationship, it's more complex, but still we are able now to derive a model and to interpret the capacity measured as a load sensor. Conclusions. Sensing machine elements, they are still far away from production, but they allow us to measure in new possibilities, new locations, and they provide valuable information for the CPS of different levels in our system. I have to shorten a little bit to keep the time. However, there's disadvantages. The technology readiness levels are still low for most of those concepts. We have, for instance, to cope with the data and energy supply and transmission out of rotating system or even electrically encapsulated systems. How do we get energy in and data out? Future research challenges. We have to solve the question of energy supply. We have to find ways to communicate with our sensor in the rotating machine element, for instance. We have to understand the sensory behavior of our systems. What about tolerances? What about the data processing? We have to understand what the impact of our sensor integrating machine elements on the system is, what tolerances have in terms of influence, how the functional reliability can be achieved. Yeah, and the idea is to take our machine elements, speed gears, bearings, feather keys, screws, whatever, provide them with intelligence, with energy storage, and end up with sensor integrating machine elements as potential accelerators for the digitalization of our mechanical environment.